So yeah, apparently from the title, we can tell that today we'll just basically talking about statistics and machine learning and when to use each and how they can be combined altogether. So first of all, of the overview, yeah, we'll talk about classical statistics in Wolfram language, talk about how to use our function to do basic statistics models to compute with distributions, and there are a lot of built-in distributions. And the second part is machine learning, which will give a short overview of what is machine learning, what are the examples of machine learning, and how it can help with analyzing data. And the next section is neural networks. Again, it will be the definition, and then we'll look into a specific neural net to see how it's designed and how we can work with it. And the last part is to bring it all together. We'll talk about the combination of statistics and machine learning. All right. So first of all, Wolfram language. So yeah, it is a highly integrated and symbolic language that basically you can do everything in Wolfram language just by opening this software, like exactly like what it is currently on my screen. Open this notebook and then start typing, and then start to coding in here, and we can pull data in, and then it'll get stored here, and then we can process from that part. So yeah, that's the basic setup of Wolfram language. We can now have one example to see the integrated nature of Wolfram language, from bringing in data and to like analyzing, like visualization, all of that. So the first example is the food hygiene map. So here we have all of this data. So yeah, it's a UK government API stuff. So we're just pulling the data, like what was the restaurant's name, and then what kind of business that is, and this it's the most important one. We're looking at the hygiene, the food hygiene rating, and then of course it's having some address information, so we can map it to the map. So here is the map, and we can see the legends here that the green ones are the better ones, and then yeah, when it's red or pink, then it's mostly concerning, and I would assume that the black means that no data yet. So as we can see here, most of them are green, which is a good sign, and like when it start to goes out to like this area, it's just not great. So this will help us to visualize the data and have a better understanding, like, oh, I probably like just for the hygiene reasons, I probably should not visit this area just for safety. And we can also put it in a heat map to see the trends of Oxford. And again, like if it's orange, deeper orange, then that's fine. But if it goes to blue, that's more concerning. So yeah, like this area in Oxford, we have a lot of restaurants. All right. And yeah, the example for Oxford is just a smaller pipeline that we built. And now we can query for the national map because we have the pipeline built already. And the whole nation map will just be the same. So it seems like for bigger cities it is more concerning, and for like rural areas, like the food hygiene rating is higher. All right, and we can also do some data analysis and put it on a more data vibe plot here. So it's like, as the town size is smaller, the rating is higher, and then when it goes goes to a bigger town or bigger city, and then the hygiene rating is just going down. And the next example is about the London accidents. So again, a similar workflow here. Similar workflow. So first of all, we get the data set put in. And then now we can again draw the map because we have the location, the coordinates for that. And yeah, seems like, yeah, this time those are, yeah, severity, slight, or like major, I would assume. So like the green one, I would assume that there are like smaller ones. Yeah, we also should have some legends here to help us to understand. And seems like here at the intersections here, it seems more concerning. And also here, because like you can you can see behind the map that this intersection is extremely complicated. Like no wonder why there are more accidents happen here. And yeah, this is just another styling of the map, and depending on what you will need, so different style of maps will help you better understand your data. So yeah, that's the integration part of the Wolfram language, and now we're talking about the symbolic computation of the Wolfram language side. So the symbolic nature of Wolfram language means that all data is stored in a similar manner, which here on the left you can see a math equation, and on the right behind the scene, when it's in the code form, it will just be a head comes with arguments, and again when you move one layer inside, it will still again be head when with arguments. And that's a math formula, and data is also the same thing, even though it looks like a table here, but behind the scene it is data set and with a bunch of arguments. Also this graph, even though it doesn't look like anything on the left, anything on the left doesn't look like anything on the right. And also images, it's, yeah, behind the scene it will just be an image with a bunch of arguments just telling, oh, where is this dot should be what color, something like that. So yeah, everything, this document, graphics, 3D graphics, sounds, neural nets, programs, and even this current interface, this tab thing that I'm clicking through, is also the same structure with this hat called tab view with a bunch of arguments and then layers in. So yeah, what does this mean for statistics and data? I will show in a second. So yeah, now let's talk about the classical statistics. So first of all, statistics, it's a lot about distributions, right? And so Wolfram language supports a large number of known statistical distributions, and we can see from here. And yeah, these are all the distributions that's already built in and supported. So yeah, last time I checked, there were about 170 distributions, but we do have regular updates of the language. So I would assume that there will be more to come. And distributions are handled symbolically, which means that every distribution will have a head, like a normal distribution. And then it will have some arguments right here. So let's look at this. So for this specific normal distribution, if I'm not specifying anything, it default to this. Let me open the documentation page here. All right, so for normal distribution, like you can see in this form, it will represent a normal distribution with zero mean and unit standard deviation, which it's like if it's written in this way, it will be normal distribution 0, 1. So yeah, in Wolfram language, everything will look like this. Let's just say we have a normal distribution, we have a histogram distribution, empirical distribution. Everything will look like something distribution with the specific arguments. So what does it mean by symbolic? Is that we can have all of these distributions and then apply other function to this. So it will just be distribution 1 and distribution 2, and then we can do the basic statistical analysis like PDF, CDF, variance, like all of that. So here I assigned my normal distribution to this variable called dist, and what I'm doing here is that I wanted to plot the PDF plot for this distribution. I can substitute this dist with any other distribution. It's like for some other languages, I believe that, let's just say if you have normal distribution and you will have another function maybe called normal distribution PDF, which only applies to normal distribution. And then maybe you have a histogram distribution and you will have another function called histogram distribution PDF, something like that. But yeah, in Wolfram language, there's only one PDF function that you can put all of the distribution in it. So yeah, that's the basic idea. And yeah, as speaking of distributions, there are a lot of computable properties. The variance, standard deviation, skewness, quartile, PDF. We've seen that, CDF, and this one. So here, this Q, we didn't assign any values to it, so it's symbolic as for now. And the equation came out of that was just a representation of with Q in it if we assign a value to Q, and then we can see the half quartile of this normal distribution will be at 0. Let's just say 4. That will be like easier. It will be yeah, it will be the same as here. Yeah, this is the quarter, this is the half, and then this is 3/4. All right. So yeah, that's just some basic properties about distributions. And so yeah, I have some questions from my other screen. Let me read it. First of all, it's from Michael asking about the map, and oh yeah, yes, I believe so. Or you can make it, or at least you can make it bigger for it to pop up more. But yeah, I don't remember it from the top of my head. But in Wolfram language, there are like so many ways and so many options that you can fine tuning a map. So yeah, that's a good question. And another one from Philip. So how difficult it is to add custom defined distribution so that commands like PDF see it? Well, we will cover some of that in this webinar like later, and I would say it's pretty easy in my opinion. All right, let's move forward. Computing with distributions. Well, first example is the basic normal distribution. We're generating some random variate from this distribution. Means that this 100 points are all based on this normal distribution. And now what we're going to do is to use this function called estimated distribution. So this one is it's with the given data, and then we, as human, we guess, oh, I think this is a normal distribution with A and B as the parameter, and I would like the machine to estimate what distribution it is. So yeah, I couldn't recommend more about the documentation center we have. So yeah, have a lot of examples and have some more detailed explanations. So yeah, if have any questions using Wolfram language, please consult the documentation center. But here, as we've already guessed, the distribution is normal distribution with the mean being A and the standard deviation being B. So now, after this estimated distribution read the data, so it gives us the result. So this should be a normal distribution with mean like this number and then standard deviation being like this. So it's a little bit off than what we originally have and what we originally generated. But yeah, that's like data feeding. So now let's see if the data is actually fitted into this distribution. So yeah, it's like a little bit less than 90%. I would say not really. I've seen better. So yeah, now let's look at the probability of x when x is smaller than 3. What is the probability of x belongs to this distribution? So it's giving us a symbolic representation of the probability. We can also ask for the numerical result, which is this 99.8% chance that x smaller than 3 is on this distribution, which yeah, totally makes sense when it's the normal distribution with mean 1 and standard deviation, mean 0, standard deviation 1. And we can also see the expectation of this 2x plus 3 to be 3. So yeah, and I do think this estimated distribution, every time we evaluate it, it will be different. Oh, it's not. So yeah, I guess it's just the like this set of data might be a little bit like over to one side or so. But yeah, with different data set from the random variant, yeah, there are a lot of randomness in between this. So yeah, sometimes it will do better. Sometimes like, yeah, the data is not great. Then what can we do, right? All right. So the next example is a real life example, the Old Faithful Gather, where which it locates in the Yellowstone National Park in the States. So yeah, it's a water version of volcano. It erupts, steams, and hot water out, and there will be like a time gap in between two eruptions. That's what's about this waiting time. All right, so now I'm querying for this data set. So you can see it's like 79 means that there are 79 minutes in between the two eruptions, and then 54 is 54 minutes, so on and so forth. So now we have this example data. What we can do is we can draw the histogram of the data. So we can see here, it looks like to us, with just wild guessing, it looks like two normal distribution combined together, with like some of them falling to the 50, 60. This is the first normal distribution, and then here is the second normal distribution. What we can do here is to build our own customized distribution. So as for here, let me clear out my variable first. So as for now, what we're having is, now, because it visually looks like two normal distribution, let me build this one as I have this mixture distribution, and then the first argument we'll put aside for a second, and let me talk about the second one. This is normal distribution 1 and normal distribution 2. This first normal distribution has its own arguments, and then second normal distribution has its own arguments. And then we can look back at the A and B, which means the weight of these two different distribution. I would say these two look like half and half, or like maybe the first one is a little bit bigger, maybe. So yeah, now we can have this mixture distribution, and remember that it's just another distribution. It's like something distribution. It's a distribution. Now we can apply the estimated distribution to this whole new distribution we just made, and giving it the data. The data is just waiting time data, and then the second one is the the guess we have, and then third we're gonna provide some guidelines of like where you should try to match the data. And as I said, A and B are the weights, so A and B are like half and half, and C is the mean of the first this hump, and looks like the mean is like 50, 55, and standard deviation will just make a wild guess. And then the second distribution with arguments E and F, which E is the second mean, looks like 80. Standard deviation just gave it a 10. All right, let's see what we get now. So as we're running the code, it gave us the mixture distribution. As the first one is the weight is like 40, 60, which yeah, makes sense. And the normal distribution, it's this one is the 54 with standard deviation 6. And the second normal distribution is this one with mean 80 and standard deviation about 6 too. So let's go back to, it's just another distribution, right? So now what we can do is we use the exact same code. We're just putting the distribution here, but like all the PDF was the same. And we're just showing the histogram like this one, and also showing the distribution like right here to see how they fit together. And for data analysis purpose, I would like to know how long will I have to wait until I see the water erupts. So this one is querying for my waiting time is bigger than 80 minutes was the probability of that. It will be 32% of chance that I'll have to wait more than that. And again, when we have one distribution, it could be something distribution, we can always use the random variate to generate random data points on belongs to this distribution. So these are the chances that like for how long we would wait based on this model. We can also again check how is the waiting time fitting the distribution. This time it's like way higher than the previous time that we have is like 94%. So yeah, based on this model, then we will have a better understanding of how long and what are the chances that we're waiting there. All right. Yeah, that's just about some basic understanding of the distribution. And now I'm going to talk about these more complicated multivariate distributions. We have the discrete ones, and then we also have these continuous ones, and all of these are built in. And I'm just showing some examples. Yeah, the first one is the multivariate hypergeometric distribution. Yeah, I just suddenly remember that last time I checked, I think this might be the longest function name in Wolfram language. But yeah, that's just a fun fact. Let's look at the code together. So yeah, this is the distribution. And then what we can do is we want to draw the PDF of it. And then now, because this multivariate, so we have to do it in a 3D plot. So yeah, this is basically means like sampling without replacement. And like I have 2 boxes. And I need to pick out like 6 balls in total. And I have 1 box of red balls and 1 box of blue balls. It's like, what's the probability that, oh, I just pick 2 from the red ball and then pick the other 4. So yeah, that's one distribution. And then this one is called binormal distribution. And please note that it's binormal, because the first time I read this, I read as binomial. But yeah, this binormal distribution, it's like 2 normal distribution combining together. And as you can see from the syntax here, it's here is the first normal distribution, and then this one is the second normal distribution, and then this one is like how they the correlation of x1 and x2. So here you can see like from this side it's a normal distribution, and then if I plot it from this side, it's also a normal distribution. So again, it would be the PDF of this distribution, and then all the other things are just cosmetics details. How do I want it to be colored? And it will just be PDF of a distribution, and then we plot it out. All right, the next example is it's some data distributions with histogram distribution. Oh, I think it needs a second because it's generating 2 pictures, and we can see that we have the PDF and CDF showing all together. And this one, in my opinion, it's just the outline of a histogram. And the next example is empirical distribution. This one, it's like based on observation. Like we have the sample size 100 here, and then each sample it's just 1% of chance. And again, we have the smooth kernel distribution. This one is just the like the smooth out of the histogram. I think this one will demonstrate that. So yeah, all of these examples I'm showing is just to tell you how easy it is to plot the PDF and the CDF of this. And again, they're just something distribution, and you just put it like right here and then substitute it with some other distribution, and then you'll get the same result. Well, based on the differences of the data, but yeah, you get the same type of plots. All right, the next examples are these meta distributions, which is the mixture of existing distributions. And again, we can apply the same trick. So this one is truncated distribution. Let's see. Truncate the value to an interval or condition on the interval. And again, we're just doing the plot and the PDF of this. All right, let's see what we get. So the truncated distribution is this blue one, and then the normal distribution is the yellow one. So basically, truncated distribution means that everything in this truncates, it's still the probability is adding up to 1, but everything is just got smashed into this range. And we have a similar distribution called sensor distribution, which I'll show a left sensor distribution first. And as we can see here, it's not smashing into one range. It just cuts off the left side of it, the left side as how we want it. And the whole build up of this manipulate was enabled by, we can just plot the CDF right here, and just asking for A to be in this -3 to 3 range. All right, and there's the right censored distribution, which is the same. We're just cutting it from the right. So yeah, this time it got cut to the right. So yeah, this one, it's usually more use cases are in medical experiments. Let's just say there's a disease, and then there's a medicine that can help cure the disease. And when the patient is more than, like, let's just say 7 years old, it would consider like that's already like everybody survived, because more than 17 years old, there are other chances that this person could have some issues. But yeah, that's where it got cut it, and then everything on the right is considered. All right, good. We're all good. All right, I hope that gives you a basic idea of how statistics and distributions are handled in Wolfram language. And now we're looking at machine learning. So when do we use machine learning, and when do we use statistics? So yeah, if for statistics, I believe that when we have like single dimension or like two-dimensional data that is easier to handle, and we have existing models that we can try to fit them in, then yeah, we goes to the statistics way. And for machine learning, it will be higher dimensional data. We have a lot of data, but we have a poor understanding of what this data are doing. And then that's where we introduce machine learning into the analysis. All right, so what is machine learning? Machine learning is a computer, a machine model learns from a set of data. So the model is a program with parameters, which say like ax plus bx square plus something something, so on and so forth. It could be extremely large. And the learning is the tuning parameters to fit the data, which means that for a good machine learning model, it would have reasonably big parameters, and also a reasonably big number of the data set of the data. So let's look at this cat and dog example here. So we have this inputs of a cat and a picture of a dog, and then so on and so forth, different pictures of cats and dogs, and then got labeled. And then we put into this thing, this map net-ish thing, which is our model. And then the model itself will calculate the parameters and then give us the result. So in the end, machine learning will just be data fitting. And a model should not underfit or overfit the data. and should be generalizable to others, to other unseen data. So for this one, let's see if my fit is my degree of fitting, which this one is only like 2 parameters, and I'm fitting, which is reasonable. But if I move my degree to be a bit higher, and as for this one, it seems like more data points are on this fitting line. More of this. Okay, getting better and better. And then again, it's getting a little bit complicated. And but yeah, we're still seeing a good trend. And if we're having a point in between, like right here, it'll basically fit in or near the line. But if we now go into the extreme, like more parameter, better. But now it gives us a overfitting model, which, as we know, the trend will just somewhere look like this. But however, like for here, it went into those extremes. Let's just say we have some points in between these 2 points, saying like right in the middle. And then based on this model, it will predict it that I'm like way under, like probably being here where my cursor is right now, which actually hurt us to get the prediction. So yeah, so a model should not underfit or overfit. That's our goal of using machine learning. All right, so yeah, here I'll be very quick, just so that you're not very familiar with machine learning. There are different types of machine learnings: supervised learning, and unsupervised learning, and reinforcement learning. Supervised learning, it's the is that you when you're marking the data, I already have the result. Like I have some cat pictures that I label it as cat, and I have some dog pictures that I label it as dogs. So I tell the machine like what's the right answer about it, and that's the input to output mapping from examples. This is the most common type of learning, and yeah, the next part is the unsupervised learning, which only has inputs. So one example would be I have a bunch of pictures of cats and dogs, but I do not label them. I would like the model to learn from that. So usually this is used for like feature extraction. I'm not too sure about these 2 animals. Can you categorize them? And the machine at this point wouldn't even understand what's a cat and what's a dog. It would just say, oh, these pictures looks about the same, so they're one category. And then those pictures looks about the same. That's the second category. So yeah, that's the unsupervised learning, and used for finding patterns and then finding the different features in unlabeled data. And another type is the reinforcement learning. The model will get feedback from its environment. The use case of this is like training those robots. It's like if the machine works correctly, it gets 1 point of doing right. So it will learn from I didn't fall, I did it right. So it will tend to do that pattern more often. So yeah, that's the 3 different types of learning. So yeah, now let's just show some small examples. Yeah, some of them are a little bit outdated, so I'm not gonna do it live. Yeah, first of all, it's the image search, and the second one is recipe classification. it'll determine the likely source of a recipe based on its ingredients. Let's just say egg and tomato. Yeah, because this one is like pretty generic. Let's see what we're getting. All right, so yeah, let's see like because it's pretty generic, so the chances of that it's being like this top 5, top 6, it's almost the same. All right, the next example is the text character recognition. I'll recognize a handwritten digit. Let's see. Let's start for a 5, maybe. All right. As I'm drawing, it sees it as a 1. And now, even though I know that I'm aiming for a 5, and you can see that I'm trying for a 5, but it's still hesitated if I'm doing a 4, just because it takes in the whole thing to analysis. It's not predicting what I'm doing. And now it looks more like a 5. All right, the last. All right. I'm just making it a little bit extreme so that it get confused with a 3 or a 5. And now I'm apparently a 3, but I'm going for the 5. So yeah, there are limitations about machine learning. As you can see that I write a 5, but maybe my pen was a little bit broken, and I just leaked some ink right here, and now the machine start to see it in a different way, and it's not actually understanding, oh, this 5 is the actual thing I'm looking at. All right. Yeah, the next one is text analysis. It will just determine the language and sentiment of a piece of text. And this one, the image generation. All right. Let's see. All right, I have this 3 different styles. I'm just gonna restyle this Mona Lisa to be the Kandinsky style. And this one, I'm restyling the Mona Lisa for the Monet style. Derive missing data. So yeah, this one is to color the image, which we gave a black and white image of the dog. And this one is referring to this neural net in our neural net repository, which I'll probably show later. But yeah, this one is using this neural net model, using the model and then giving the data, this black and white. And I believe this model is trained to actually recognize the item and then the background, and then make the decision to see how to recolor them. And this one, it's similar. It's also asking for a neural net, which is a model. And we're still seeing the same dog image. So yeah, now it sees the depth. Like it's a 3D. The grass is flat and then the dog is out. And for this one, we could do. Oh yeah, let's give it a second. We can do a satellite image and to make it into the map style, which yeah, here as for our human eyes, we can see the intersection looks a little bit out of line, but here for a machine, it will just be a little bit harder to comprehend. And this is the investment choice. So let's just run it. So basically, I'm just feeding some data to it so that it can quickly use a classifier to learn about that and to decide what investment I should do. Well, not me, this PhD male person should do. And we can also gave a plot of like for this PhD, it's from age 0 to 60, a male person in England, what should I do? And here we can simply deploy this to the cloud, which Wolfram Cloud is also a powerful platform that you can deploy your model, can deploy a form, or you can put your API right up there. So just so if you want to pull it out in your family party to give suggestions to other people, well, that will be pretty useful. Let's just say, yeah, I'll say what I get. All right. So yeah, now that you have the basic understanding of what machine learning can do, and we will look more detail into how to build the machine learning models. Well, first of all, we will talk about the supervised learning with classification. Again, it will just be the cat and dog example. We will need to prepare the data and sort it into training data and testing data, and create a classifier, train the classifier on the training data, test the classifier on the testing data, and measure the accuracy of the classifier against the testing data. So yeah, the important part here is to sort the data into training and testing data. Well, just imagine that I'm not handling the data before, and I only have one set of data, and I gave it to my model, and my model learned from it. And again, I'll ask for, in the same data set, I'll ask for the information, which my machine actually have the answer already because it has seen it before. It's just like student going to test with like all of the questions that they have studied before. So there's no point to see if our model is doing good or not. That's why we need to sort the data into training data and testing data. So yeah, here is a simple case that I have an extremely small data set, and 1 and 2 are categorized as A, and 3.5 and 4 are categorized as B. So now I'm training a classifier function, and my input is numbers, and my output are classes as either A or B. So let's see. Let's ask for the probability of this, my input to be 1.2, and then the output will be A. The probability of that is like my model is basically extremely sure that my data point will be categorized as A, and then has like nearly zero probability of being in the category B. So yeah, that's because 1.2 is like right in between this 1 and 2, which the machine can be more sure. But what if we pick something between these 2 and 3.5? Let's do a 2.8. And now it says that, oh, the category is going to be, but let's see behind the scene. What's the probability of that? And this time, the machine is not so sure about it. I will say, the percentage of being A, it's about 35%, and then the percentage of being in category B is 64% of chance. So basically, machine learning in the end will still be probabilities, will be like how likely it will be on the distribution. All right, so the next example, it's this day and night example. First of all, I'm training some I'm training some this classifier with this data, and now this is a set that is not included in my training data. So let's just see how my model is doing. All right, so it's seeing the last three as nights, which is correct. And then the first three, oh, is one day and night and day, which it says, oh, this picture, I see it as nights, probably because we do not have enough data, enough training data here, and all of the night picture are like something dark with those yellow lights here, and you can see in this picture it's dark color with some yellow. That's why the model get confused. So yeah, there's a balance in between how many data points that we needed to train a good model. Yeah, there are some trade-offs. But yeah, for this one, it's definitely too small. All right, the next example is about Fisher's iris data. In this example, we will look into some more detailed analysis on the result. So the training data and testing data, this is the example. So I believe here we have, I think it's the sepal length, petal length, something that I currently don't understand. But yeah, everything was collected into these numbers. And then we have this set of number and we have the label, the result. They are either setosa or versicolor, or there's another one, virginica. So now we're training the classifier again by feeding the data into it. And now we're giving the testing data to the model we trained. And then we're looking at some statistics here. So we're giving 45 examples of the testing data, and the accuracy is like 95%, which is pretty decent. And yeah, here are just some more mathematical details. And the important one is this. It's the confusion matrix plot, which was telling us like this. Okay, vertical is actual class and then predicted class. So for here, so this versicolor is the worst predicted one that got predicted into Virginica. There are like two cases. Oh no, backwards. But yeah, you get the idea. So yeah, we can also correlate the measurement just as how it is now, not in this fancy table. And also can query for the confusion matrix. And here we're asking for the worst classified example. Okay, please give me 3. And then we can see it's all this versicolor ones got predicted wrong as Virginica, or it's like it's not so sure that they are versicolors. And the best classified examples are this Sentosa examples. So yeah, from here, these numbers and then this matrix are actually helping you to understand what's going on in my model, if it's working. Well, I mean, like for the model, we couldn't actually understand how it works, but we can understand if it works. If it works, that's all we want. So here, when the worst classified example are versicolor, we will need to think about what can we do to improve that. Are there not enough versicolor examples there, or in some way this is confusing? So yeah, that's when we need to look back into the data to the beginning point to see if there are other ways for us to decide that can help with the classifier. All right, the next example is the machine learning, the prediction example. So first of all, again, we use a simple case, and we have this one point, and we can predict the second point. Now we have this predictor function trained. Again, it is so simple. It will just be this one function, and then you put the data in. This time, I want to see where 1.5 is, and it was telling me that it's also 2.4. Okay. And this distribution is telling me like where 1.4 is sitting at. So it should be sitting at this in this normal distribution. And now, because this is a distribution, which means that we can apply all the statistical that workflow here, which again, we're seeing this PDF and we're seeing this plot. And we're doing the same thing. We put the distribution right into this. All right, so it will just give us the regular distribution plot. Okay, the next example, it's the wine quality example. So here we're just getting some training data, testing data, and I believe the data looks like, let me see. Yeah, the data looks like, well, there are some different, these are the percentage or the gram of some different chemicals, I think. And what we're predicting is the score of this one. If it's 6, it's more than okay, something like that. All right. So now, again, similar thing. We use this predict function to train the data. Yeah, this time we have that monitor for a little bit longer, but not long enough because we don't have much of the data points. And now, this time, for the predictor measurements, we can also see this this plot. So I believe for the diagonal, it would be the perfect prediction. And what we have here, because our actual values are in digits and like 6.2, but our predicted value is in digits like 6.2, 6.5, something like that. But the actual value is in integer numbers. So that's why it looks like this. But look at the trend that it's almost on diagonal. That's okay. And somehow this too looks like some extreme outliers. We will need to look into that. All right. I think we can also query for like all the result from there, the standard deviation, the comparison plot, just the diagonal plot, if you just only need the plot. So yeah, this will help us to understand the data and look at the outliers to think like how we can improve. And then yeah, the next one, it's about the same idea, but I would like to cover more things. So yeah, we'll skip this example now. And let's look at the unsupervised learning feature extraction. So as for now, machine learning, AI, neural net, all of those are basically like used interchangeably, but like in the end, it will just be a model that learns by itself from the data. So here we're showing a basic map of how how the training is working. Let's see. So first of all, we have this training data, and then we put them into this encoder, so it becomes some vectors. Well, you can take the encoder as a human language and machine language translator. So it gets our training data into something into vectors. That's where the machine could understand. So yeah, now we have this base model, and we'll read all of this data and do all this training. And then we have a trained model. And once we have a trained model, we will try to see, let's see if it works by giving it some test data it's never seen. So my test data has input, and again, we go through the encoder to translate it to vectors so that the machine understand. And then the trained model look at our new data and say, how do I answer this question? And it will give us back some vectors which we couldn't understand. It needs a decoder to give us to translate back to human language so that we can understand. So we have the answer. So yeah, that's the basic idea of how this training and this model data, how they interact. All right, this example is about dog breed, which we will import some dog images from our folder. Let's give it a second. All right, now let's look at some cute dog pictures. And what I'm doing here is that I would like to extract the feature of these dog images, which I have this feature extractor function, which you can take it as a model. And now we ask this model to see this dog picture, and it translated into something that we couldn't understand. It's like a lot of vectors, but that's how the machine sees an image. And we can then see the feature distance of these two pictures. Well, this 30 might not make sense as for now, but if we compare it with this one, so these two dogs looks similar. They're both hound dogs with bigger ears. They have similar colors, right? But these two dogs looks extremely different. One is the hound dog, the other one is I'm not very familiar with dogs breeds, but looks like a smaller dog with up pointy ears. So that's why the feature distance here is 40, and then this one is 30. And if I do this, and they're exactly the same, so the feature distance will be 0. So this is how machine sees it. It translated into a vector, some numbers, data sets, and it compares and calculates the distance in between those. If the distance are smaller, means that they're more close in features, but if the distance are bigger, then they're more different. So we can use this feature space plot function to actually visualize the images, like where they sit and how far away they are from each other. Yeah, let's just give it a second. All right. So yeah, here you can see, before we dive into the details, you can see these dogs are put into like 3 categories in general. Like this one is very separated out, and then this one, it's one category, and this one is another category with something like in between. So yeah, let's see what's here. They are the longer hair hound dog. Yeah, they mostly look the same. And what's here? Here are the I guess, are the smaller dogs with bigger eyes, pointy ears. And what's down here? They are the hound dog with shorter hair and long ears. All right, now what we're curious is what's in between. So here, this one, it's like not showing the face of the dog. That's why where the machine might be confused. This one has a human in it. This one has another human in it. Yeah, this one is have a fan. But yeah, like you can see like more going down more, it looks more like the hunt dog with bigger ears. And because this part of dog have long hair is like a total different dimension. So yeah, that's what a feature space plot can help us to understand the data, just to see like which ones are similar, which ones are in the same category. All right, now let's look at the neural networks. So yeah, again, machine learning neural networks, these are like interchangeable word using, but it's the same idea. It's like we have the inputs, we got the input got in, and then the neural networks are layers of regressions that feed into each other so that it mimics the architecture of the brain. And it'll be multiple layers of fitting, which and the alternating linear or non-linear layers. Yeah, we do have another webinar talking about neural networks there, and it will have a more in detailed explanation for that if you're interested. And yeah, these are just some specific layers that serves for different purpose. Some of these layers are better working with images. Some of them are good at like dealing with like numerical data, something like that. All right, now let's see what we can do with all of these layers. So we have so many building functions that's devoted to build a neural network. And these are the building layers that you can just grab and use. And we also have functions that dedicate to build neural networks. So like how to put the structures together. All right, there are a lot of freely available neural nets in the Wolfram neural nets repository, which I'll show later if we have time. And now I would like to show how we can work with neural networks. So first one is the LeNet. It's the one that we used for the recognition of handwritten digits. So first of all, we will need to bring the LeNet coming in. So here we're just calling the name of that by using this net model. And now LeNet, this variable will remember this being the net. And we're just giving some testing data to it. And now, as we can see, the first one is the handwritten digits, and the second one is what it got processed as, like the prediction through the nets. And as we can see, like everything looks pretty reasonable here. All right, that's an existing neural net, and we can give it new data, and let's see how it works. So now I'm giving it some blurred data. Let me just show that. So yeah, I'm just have some typesetting letters, numbers, and they're just blurred. It's not handwritten anymore. And let's see that this time I asked LeNet to recognize this. It's doing a pretty bad job. Like this one got recognized, this 0 recognized as a 2. And yeah, we can see like about half of them are not accurate. What does it mean? It means that our LeNet was not trained for this purpose. So if we actually want LeNet to recognize our just blurred typesetting numbers, then we will need to train the LeNet with our new data. Then it will do a better job at recognizing these similar ones, but not the original LeNet. All right, now this one is the new LeNet. It got trained more, and now we can see this time I'm feeding it this one, this one I generated, and it's giving all the correct information, which is something that we actually shouldn't do because, again, I've already handed the answer to the model for it to learn. Of course, it's going to give me the correct answer. So here we're creating some new data so the LeNet has never seen before, even though it's, again, more trained, it has never seen before. But also in the similar idea, but in a different font family, but blurred. So this time I'm giving the testing data to the, again, trained LeNet, then it's still behaving pretty decently. And learning new data doesn't mean that my net lose the power of recognizing old data. So I'm just giving it some other like old handwritten digit, and it's still performing pretty well. All right, that's from the data training side of how you can modify your neural net. And here, this example is showing that how we can rebuild the net so that it's performing another task. So yeah, I'm not gonna go into much details here. So basically, we're substituting one layer of the net, and then we're giving it other instruction, saying like, oh, instead of seeing this as 1, 2, 3, 4, 5, I would like you to categorize them into Eastern and Western writing digits. So what I'm doing here is that I'm not going to expand this, but as you can see here, we have some, these are the Eastern Arabic numerals, I believe, and then these are the Western ones as the ones that we're currently using. So yeah, basically I substitute one of my layers to tell it, well, stop doing what you're doing now, or doing before, and then now what you will be doing is that you learn from all of this data and divided them into two classes. One is the Western, one is the Eastern. And I have this new net designed for my new task. And I'll just train it. Yeah, here we can see the training progress, like the tracker, and like these are the error rates, the loss of the function, and the progress. So yeah, this one, it's reasonably fast, but there will be tasks that's like reasonably slow, and there are some other fine-tuning options that you can do to restrict that. So here, this modified net now classifies characters as being either Western or Eastern. And okay, so as for here, the first half of the new data set, it's Eastern, and the other half is Western. So yeah, now you get the idea of like how to alternate the neural net, we can look more details into the nets. So these are the layers inside the net network. And what we did was just, we pulled out this layer and did some modification. And if you look into the first layer more closely, there are more options here. And now this example is trying to help you understand what a neural net is seeing at different layers. So first of all, again, we pull in the model, and we would like this model to identify what is this picture, which is a tiger. So here, what I'm doing is to take the first 10 layers of the network and apply it to the image so that we can see at the 10th layer what it's the net it's seeing. Again, it's a lot of numbers, which that for me as a human I could understand. And here is also what the neural net is seeing. Again, it makes a lot of sense to the machine, but it doesn't make any sense to us. All right, so yeah, this one it's just showing the dimension of like each layer and how the data are transformed in between each layer. All right, yeah, that's the overview of the machine learning part. And now we can look back, thinking about the statistics and machine learning and how they can be better together. So with the two areas of functionality combined, new tools becomes available. The first one is called find distribution. So first of all, let's give some random integers, which it's in between 0 and 1. We have 100. And I would like to find a distribution of what these data are. And this one is apparently a discrete uniform distribution from 0 to 10, which makes sense. And I believe that find distribution has machine learning behind the scene. And it's just not about algorithms, about data feeding. It's the machine learning behind the scene. And here, again, the find distribution gave us a distribution. So for the something something distribution, I can apply all the PDF and all the variant, all those statistics tools to it. The next example is find formula, which again, we are generating some data using some steps here. So we're generating this x times sine of x and from 0 to 4 and at the step of 0.3. So, all right. So all of these numbers, these coordinates should be sitting on this formula. So now let's use this function called find formula to see what's the data with respect to x, what is the equation. All right, now it gives us the x times sine of x. Yeah, sometimes if I run it again, it might give me different different answers. Like this time it gives me like 1 times x, which it's indeed the same as x times, and we can put it in the PDF, the plot again. And yeah, learn distribution. Now, for those statistics models, it will only work on numbers, right? But this learned distribution can work on images, So I'm just pulling in this resource data. That's are some there are some images of random things like apple, animals, something like that. All right, now I'm training a distribution on the images, which I believe it will take a second. So yeah, now we can look at the monitor. For here, I'm setting my time goal to 30, but it was just a goal. It might take longer than that, depending on how the machine is working. So yeah, I can also specify the best method to use. Method goes to something, something. And yeah, as we can see, the learning curve is going down. Learning curve for algorithm. All right, now it's trained. It has this new distribution now. And what I can do is, again, all those statistics stuff, I'm generating some random variant on this distribution, which, again, to us, human couldn't understand, but they are on that distribution, which means in the machine's eyes that these are the same as these pictures. And here I'm just comparing the probability density of an image of the training set. And here I'm getting the this is from the training set, and this one I'm getting a random one from here. Oh no, I'm getting a random one from the learned distribution, and this one is the digit, and this one is totally random, not related. So we can see here the PDF of is basically, you can understand it as the probability of the chances that this picture is in this distribution, which basically means the set of the pictures. So this one is in the data set, this one's in the data set, and this one we just generated from the distribution, of course, will be in the data set. And this two with a huge negative here, then it means that it is basically 0% of chance that they're in the distribution. All right. So our last example is anomaly detection. So yeah, this is usually happening before our data processing. We would like to take out some data that's apparently doesn't belong here. So we're training this anomaly detection. We're training this anomaly detection model here, and yeah, it gave us the anomaly detector function, which we can use, which is our model. And now we want to find the anomalies using this detector function, and then to look at this data. So now this time I find the animal here, but I didn't pick this one out because in some sense this one still looks like a number written. That's where the acceptance threshold comes in. All right, here we're setting the acceptance threshold to 0.01, which I would believe that it's taking things that it's not sure, and picking those out. And I you can totally change the acceptance threshold. It's like for maybe this one, it's like there is a tiny little chance that they do not fit, they look weird, then they got picked out. And I can also like loosen my threshold so that some of these, like this 0 looks all right, this 2 looks all right, they'll get taken. They won't be kicked out. But yeah, I don't quite remember like if the threshold being bigger, like this number being bigger or smaller would be loosen the criteria. But yeah, you get the idea. All right. That's all of the material that I will have to cover today. So the summary will be, we look at the symbolic computation, and then we look at the statistical framework. We can have a distribution. We can apply all of functions to those for analysis. And we have functions for machine learning, supervised, unsupervised. We look at the neural net together, and like later it's the full automation as well as fine-tuning capability. And then like in the end we look at how to make statistics and machine learning together. All right, so yeah, I'm almost running out of my time, so here are some resources that you can use. There are some WolframU courses, webinars about machine learning and LLMs if you're interested. And the documentation is also very helpful to help you start it with machine learning and neural networks. And you can see the revision history of Wolfram Language. We've been keep working to add more things to the building functions. And later it's a book talking about machine learning in specifically in Wolfram Language and in Wolfram Language examples. All right, yeah, that's all from me for today. Thank you